Hello, my name is Stavros Vougioukas. I'm a professor at the Biological and Agricultural Engineering Department at the University of California, Davis. And I'm going to present to you today challenges and opportunities for robotic harvesters and harvest aids. I would like to sincerely thank the organizers of the conference for the invitation to present, and I'm looking forward to a very fruitful and interesting discussion afterwards. Now, in case you're not familiar with my institution, UC Davis and the Bio-Ag Engineering Department are located in Northern California, about 1.5 to 2 hours from San Francisco, depending on traffic, and about 2 to 4 hours away from the Central Valley of California, which is one of the most productive and intensely cultivated regions in the world. The department is about 100 and something years young. It was founded in 1915. Now, California produces a lot of different crops, specialty crops. And as you see here, apart from milk and dairy products, which are #1 in production, we produce almonds, grapes, pistachios, lettuce, strawberries, tomatoes, walnuts, and lots of other fruits and vegetables, and providing them for the entire US and actually the world. Now, my lab, the Bioautomation Lab, is very active in 3 major areas. One is collaborative robotic harvest aids. The other is mechanical and robotic fruit harvesting. And finally, technologies for autonomy and mechanization in orchard operations. Now, given the audience here, I don't need to repeat that one of the biggest challenges of our times is to increase the supply of food, feed, fuel, and fiber in a sustainable manner. And that supply chain encompasses all the stages going from breeding to farming to processing and distribution. And of course, they include both crops and animal production. And this supply chain needs to undergo major changes. And one of the key promising technologies for that is robotics. So agricultural robots, from a bird's eye point of view, offer automated sensing and actuation services. What are those services used for? Well, in agriculture, there are 3 main application areas. One is high throughput phenotyping, whether this is for crops, mainly crops for the time being, but also for animals. The second area is precision management, either precision farming or precision livestock production or aquaculture, applying the right amount of input, the right type of input at the right place, at the right time. And then finally, last but not least, is labor savings. This is a very important area for agricultural robots. And I don't need to remind everybody of the dire situation with farm labor shortages in many, many parts of the world. Now, today's presentation will focus on fresh market crop harvesting. And the main reason is that despite all the mechanization in agriculture, every single piece of fruit or vegetable landing on our plates most likely was hand harvested. Why? Well, main reasons are that these fruits and vegetables don't necessarily ripe at the same rate, so they need to pick selectively. Also, they need to be picked with near zero damage. We should not scratch them or bruise them in any way to reduce their shelf life. Unfortunately, today's consumers also want perfect products, so even the smallest blemish lowers its market value. And finally, and very importantly, they must be picked in a cost-efficient manner. Otherwise, it's not really practical. Now, what about robotic harvesting? Everybody talks about that. Bottom line, the feasibility of robotic harvesting was established in the 1980s. You get a camera, you get a robot arm, write some software. People were able to show that you can pick fruits. However, research in robotic harvesting and mechanization in general was put in the freezer for about 2 decades, mostly for socioeconomic reasons. But it picked up relatively recently for the last 15, maybe 20 years. And the reason for that takeoff of research and development is one, the farm labor shortage. This is the key driver. But also because now we have in some crops machine-friendlier crops. For example, instead of having large, three-dimensional apple trees, we have now orchards that look like fruit walls. All the fruits are hanging nicely in a structured way, easier to find and pick. Also, hardware is definitely better and cheaper. Better meaning faster, mainly large storage also. There have been a lot of advances in algorithms in perception and control, robotics. And of course, very importantly, there is an abundance of R&D funding from federal or state funding, but also from private companies and venture capital. So the question is, why after so many years of R&D in this area, for most crops, fruits and vegetables, fresh market fruits and vegetables, there are no commercial robotic harvesting units out there? Well, the truth is that robotic harvesting is not easy if you want to do it in a cost-efficient manner. We know from studies that the 2 key parameters for a cost-effective harvester are the efficiency and speed of harvesting. Efficiency is basically the percentage of marketable fruits on the tree that you are able to pick. So if we imagine there are 100 fruits on a tree, let's say that a percentage of those are visible by your machine or even your person who is harvesting. From that percentage of visible fruits, another percentage can be perceived by the harvesting system, right? Then from those, only 1% can actually be reached by the harvester. And from those that are reachable, only a percentage will be detached successfully, not dropping them down, not bruising, etc. And then from those, only 1% will be conveyed back to a bin or a box. So the problem here is that all of these efficiencies are multiplied. And even if you achieve high efficiency in one stage, but you have a low efficiency in another stage, the overall harvesting efficiency will be low. Imagine that you're doing 95% for each one of those stages. That's a pretty good number. But if you raise 0.95 to the power of 5, that's a 77%. That's very poor. All your profit probably lies in the next 23% that you didn't pick. So this is a major challenge for agricultural harvesting robots. The other challenge is speed. How many seconds it takes to pick a fruit, or how many fruits per second you can pick. Now, people say that, robots can work 24/7, let's leave them there, they don't need to be fast. That's not necessarily true. First of all, because there is a limited window in which we can pick for optimum fruit quality. Second, there is a whole supply chain around harvesting. And these robots don't work in a vacuum. So you can't expect that chain to be working 24/7 around the machine. So harvesting speed is important because it helps shape or dictate the cost of harvesting. And so if you're harvesting fruits, let's say it will take you some time to position yourself close to the fruit at the tree that you're harvesting. It will take you some time to perceive that fruit. It will take you some time to reach for it. It will also take some time to detach it and some time to transport or convey it to a bin. Now, of course, all of those times are added. So again, if something was not designed properly, it becomes a bottleneck. Let me give you a scale to see how important it is. An average picker on an orchard platform in California takes about 1.5 seconds to pick one apple. Now, if the robot picks one apple per second, which is, some people claim that they have done it. We don't know if it was sustainable or not. But even if we assume that this is done, then if that robot costs $500,000, it's just replacing one person. That doesn't make a lot of sense. So these are the main key challenges for harvesting robots. And we need to understand that this efficiency and speed is an interplay between the orchard structure itself and the machines and the algorithms. So it's not only technology, but it's also what we are working with. If you have trees like these on the left that are huge and unstructured, it's extremely unlikely you can ever build a cost-efficient harvesting robot. You can build one, you can write some papers about, but not a real machine that can work in the fields. On the other hand, if your apples are out there to grab and they're all arranged in a nice fashion, then it's much easier to build such a machine, although it's not necessarily still easy. And also, bringing the orchard to this form takes a lot of money. So breeding and horticulture are needed to make more machine-friendly crops, but also our high tech is needed to harvest those systems, those horticultural systems. So the bottom line is that robotics and robotic harvesting are not easy, but it's not the only solution. Anything we can do to increase the efficiency or speed of existing event systems that are based on humans can help. So I will present an example where we intervened in the transport stage to increase the speed of a harvesting system that comprises humans and robots. So here's an example. This is how we harvest strawberries in California. I say we because I've done some of it, but it didn't last long. It's a very difficult job. You're picking strawberries in this position from 100-meter long rows. These are raised beds. And once you put all your strawberries inside this paper tray, then you have to walk or run to the edge of the field to deliver the tray, get an empty one, and go back and harvest again. They are running because they are paid by piece. So the more trays they transport, the more money they make. Problem is those rows are long. And so they spend about 10 to 20% of their shift time on tray transport. So our idea and goal was to reduce that tray transportation time using technology. And we started a project that lasted about 4 years. And the end product of that project is something we can see on this slide. So these are completely autonomous robots that are going into the field to a picker. They start going to the picker before the picker finishes. They predict when the tray will be full and where. They go to the picker, and then once they're there, the picker will take their full tray, they'll deposit it on the robot goes away, and the picker resumes picking. So this is how the overall system works. And again, it's all autonomous with robot scheduling, collision avoidance, all the works. Now, how is this happening? How can the robots know where and when to go to a picker in order to get their tray? Well, what we did was that we equipped those cards with some electronics. So there is a GPS device that gives us the exact position of the picker within 30 centimeters. We installed load cells, so we know how much weight there is on this tray in real time. And all of these data are transmitted wirelessly to the robot fleet, to a main computer on the field. What does the computer do with it? Well, the computer is actually running a digital twin of the harvesting process. So there is a model, a hybrid systems model that is being integrated in real time on the server in the field. And the parameters of the pickers in this model are being identified in real time from the data. So this hybrid system describes how the robots and the pickers operate. Now, from this model, the computer is able to predict where and when the pickers will need the robot. So they need to predict that because if they were reacting to a request, they would have to travel a long way to the picker and thus introducing wait time, which is not good. So what happens then is, once they predict, the problem is that people are unpredictable, right? They may take a little bit longer to harvest or walk. They may answer a phone call, etc. So there is a lot of uncertainty in that prediction. How do you deal with that? Well, we adopted the multiple scenario approach. The main idea here is that the uncertainty of the pickers is sampled after, of course, it has been measured in the field, and it is used to generate possible scenarios for the spatio-temporal distribution of the trade transport requests. So the digital twin is generating 50 or 100 alternative futures for how the harvesting will go. For each of those possible scenarios, the computer finds an optimal schedule for the robots, a task assignment and scheduling that maximizes the efficiency of the crew. Then, what does it do with those 50 or 100 different plans? Well, it uses some consensus function to synthesize a near optimal solution that is not the best for all of them, but it's robust and it's pretty good. So this is the system that was developed, tested, and actually deployed in commercial harvesting orchards in California. We managed to try it for a limited number of days in November where the yields were low. We used 2 robots and 7 workers due to budgetary constraints. We couldn't have more robots. We measured an average efficiency gain of about 12%. Now, this may not look great, but it's actually pretty decent, and it gives you a return of investment that's much less than a year, because these robots are pretty cheap, about $10,000. So if you deploy them in July or June or August when the yields are higher, our data and simulations show that you can achieve at least 20 or 25% efficiency gains. So this is an example of an alternative approach to fully autonomous robotic harvesting. What we are doing next is considering the following. The robots now maximize the efficiency of the entire crew, but the crew consists of slower people, faster people, older, younger, more capable, etc. The robots don't care right now. They will offer the same service to everybody. However, what if the robots were programmed to offer not equal service, but equitable service, which means they would offer more frequent, better service to people who are slower, maybe because they're older. And that way, they increase the gain in profit and money more for those people than for the fast pickers who are already making a lot of money. So this is something we already tried by changing cost functions and constraints in our optimization. And we were able to get some preliminary results that show that there is actually a redistribution of income, which can be favorable for all these workers. This is again an example of how robots can help people pick faster, be more efficient in harvesting. But of course, this can happen in different types of tasks. So let me now go and list some R&D opportunities that I see in this space. First of all, regarding robotic aids, as we saw, robots can increase work efficiency. By the way, they provide a lot of valuable data while doing that. And although everybody talks about big data in agriculture, specialty crops suffer from lack of data because there's a lot of manual operations. So that's great. Now, we do need advances, especially in modeling and sensing of farm workers' activities, because unless the robots understand what the people are doing and are able to predict what they will be doing next, we cannot optimize the operation of the collaborative system. And also, we need to incorporate those models and other issues and objective functions and perspectives into the programming of the robots so that they offer safe service, they improve the ergonomics of the people, and they may be able to offer more money to enable people to make more money in a more equitable fashion, and thus increase the pool of the workforce. So this is all, I believe, very exciting. And by the way, the applications of these are not confined in the field. Robots are working in warehouses these days. They're collaborating with people, and the objective functions in those optimizations are coming under scrutiny nowadays. So I'll stop here about that. Also, I would like to add that when it comes to robotic harvesting, we did see that efficiency and speed are extremely important. And now what we need to work on is we need to find ways to increase the visibility and perception capabilities of robots. One possible approach is to do multi-view imaging, where we get multiple perspectives of the fruits and the trees, and how do we fuse them? That's an interesting research question. Active sensing, how can we actually, how can we actually integrate the action of picking a fruit with getting camera footage from that action and increase our visibility of the fruits. Another area is large data sets. We really need to do those to improve our perception algorithms. Novel sensor could also help. There is a lot of interest and potential in high frequency like terahertz imaging and some other modalities. Also, the mechanical design and control of multi-arm robots. There is no way, I believe, that we can achieve superhuman capabilities in harvesting, let's say, 10 fruits per second if we use one arm, not even two. But if you use multiple arms, how do you design them? How do you schedule them and control them at a high level so that load balancing takes place and you don't starve them out of fruits and you maximize your performance? And how do you control them at the low level, possibly with visual servoing, in order to improve your successful reaching and detachment rates? Another area is mechanical design and control of fruit grippers and conveyance systems, because again, you need to increase the detachment ratios, the efficiencies and the speeds. Finally, we all need to remember that ag production systems and supply chains will not necessarily change or cannot easily change to accommodate our machines, our robots. So when we build robots and design them, we need to take into account that they should fit well in the existing system. Or if we ask people to change farming systems and supply chains, there better be a good justification for it. And with this, I would like to thank you for listening to my presentation. I would like to acknowledge all my collaborators in the lab, my funding agency, and Beteravia Farms for giving us the space and the time and the resources to do our experiments. Thank you very much. I'm looking forward to your questions.